All right, let's talk about the brain. Not your brain, but the brain inside every single digital device you own. I'm talking about the central processing unit, the CPU. It's the engine, the command center. Really, it's this tiny little marvel that powers our entire modern world. So let's dive in and unbox this thing.
I mean, really think about it for a second. How does something that's literally the size of a postage stamp run, well, your entire world? This little slice of silicon, it's smaller than your thumbnail, but it's cranking out billions of calculations every single second. It's the reason you can watch this right now, or play the latest games, or talk to someone on the other side of the planet. So how on earth did we get from computers that filled entire rooms to this?
To really get a grip on the modern CPU, we've got to jump in the time machine. We're going way back to a time when a single computer took up a whole room and, get this, had less power than the watch you might be wearing right now. This is a story all about things getting smaller and smaller and unbelievably smaller.
So this whole journey is really a series of aha moments, each one solving a huge problem. Back in the 40s, you had these massive computers like ENIAC running on thousands of vacuum tubes. They were huge, hot, and not very reliable. But then, in 1947, a game changer, the transistor. It was way smaller, faster, and more dependable. A decade later, in '58, we got the integrated circuit, which was like, hey, what if we put a bunch of these transistors on one single chip? That idea led directly to 1971 and Intel's 4004, the world's first microprocessor. The entire brain was on one chip. And from about 2005 onwards, the race wasn't just about raw speed anymore. It became about adding more brains, or cores, so our computers could juggle a bunch of tasks at the same time.
Okay, this is where it gets wild. This comparison just blows my mind. On one side, you've got the ENIAC from 1946. We're talking 30 tons, 18,000 vacuum tubes. The legend says it literally dimmed the lights in parts of Philadelphia when they fired it up. And on the other side, a modern CPU. It weighs less than an ounce, you can balance it on your fingertip, it's packed with billions of transistors, and it just sips power. This insane shrinkage is all thanks to something called Moore's Law, which basically predicted that the number of transistors we could cram onto a chip would double every couple of years, and for a long time it did.
So what's actually going on inside one of these little marvels? Let's crack it open. The best way to think about it is like a super efficient, high-tech office with different departments all working together in perfect sync.
First up, we have the cores. You can think of these as the actual workers in our office. An old-school single-core CPU, that was like having just one person trying to do everything. Answer the phones, write reports, make coffee, everything. Today, we have multi-core processors. 2 cores, 4, 8, even more. It's like having a whole team of workers. That's why you can have a browser open with 50 tabs, listen to music, and have a game running all at the same time without your computer grinding to a halt.
Okay, so if the cores are the workers, then clock speed is how fast each one of them works. It's measured in gigahertz, or GHz. So a 3 gigahertz processor is doing 3 billion cycles per second. For a long, long time, the name of the game was just to make that number go higher and higher. But we kind of hit a wall. Pushing the speed too high created a ton of heat and used way too much power. So the industry had a clever idea. Instead of trying to make one worker insanely fast, why not just hire more workers? And that's when we really shifted to the multi-core world.
And you can't have workers without a place for them to put their stuff, right? That's where cache memory comes in. It's a small chunk of super fast memory located right there on the CPU chip itself. Think of it like a worker's desk. It's way faster to grab a file that's right on your desk than it is to get up, walk across the office, and find it in the big filing cabinet. That big cabinet is your computer's main RAM. CPUs even have different levels of cache, L1, L2, and L3, where each one is a little bigger but a little slower. The more cache you have, the less time the CPU spends just waiting around for data, and the faster everything feels. So we've got our workers, the cores. We know how fast they work, that's the clock speed, and they've got their desks, the cache. But what about the size of the jobs they can tackle? Can they handle a tiny little memo or a giant building-sized blueprint? Well, that's where bits come into the picture.
You know, the biggest difference between a 32-bit and a 64-bit processor for you and me is all about memory, how much RAM your computer can actually use. A 32-bit system could only handle about 4 gigabytes of RAM. Back in the day, that was a ton. But a 64-bit processor, it can handle, well, look at that number. It's over 18 times quintillion bytes. It's a number so big it's hard to even wrap your head around. This is the reason modern computers can have 16, 32, 64 gigs of RAM or more, which you absolutely need for today's software and games.
Okay, but how do they do it?
How do they cram billions of transistors onto a chip you can barely see? The answer is they make them ridiculously, mind-bogglingly tiny. The nanometer process is all about the size of those transistors. It's like building a city. If you can make all the roads narrower and all the buildings smaller, you can fit way more of them into the same area, right? And it's faster for people to get from place to place. It's the same idea. Smaller transistors mean electrons have less distance to travel, which makes the chip faster and more power efficient. That's the real secret sauce of modern chip making.
All right, so we've seen the hardware, the anatomy of the office. But how does it all come together? How does a CPU actually think? Let's switch analogies for a second. Now imagine our CPU is a master chef, and it's following a recipe with lightning-fast precision.
So what's this recipe written in?
Well, it's written in the simplest language you can possibly imagine, binary. Ones and zeros. That's it. Every single thing your computer does, from moving the mouse cursor to loading a web page to rendering a crazy 3D world in a game, it all gets broken down into a gigantic list of ones and zeros. It's just on and off electrical signals.
These ones and zeros get fed into billions of microscopic little switches called logic gates. And these gates do super simple things. They perform basic logic like AND, OR, and NOT. For instance, an AND gate will only output a 1, an ON signal, if both of its inputs are also 1. It's that simple. But here's the magic. When you combine billions of these incredibly simple switches, you can perform unbelievably complex calculations. You can do everything from adding two numbers to creating beautiful graphics. It's profound complexity, all built from the simplest possible foundation.
And all of this happens in a constant, repeating three-step dance. It's called the instruction cycle. Step 1, fetch. The CPU's control unit grabs the next instruction from memory. Think of the chef reading the next line of the recipe. Step 2, decode. It figures out what that instruction means. Oh, I need to add these two numbers. And step 3, execute. It sends that instruction to the right department, like the math department, to actually get the job done. Fetch, decode, execute. This is the heartbeat of your computer, and it's beating billions of times every single second.
But, this story is far from over. The evolution of the CPU is still going at full speed. Things like artificial intelligence, massive data sets, and our constant need for better mobile devices are forcing engineers to completely rethink how a processor should be designed. So, what's next on the horizon?
Well, for one thing, we're seeing more and more specialized chips. Your phone probably already has a dedicated AI chip to help with things like making your photos look better or translating languages on the fly. There's also a huge push for extreme energy efficiency, not just so our phone batteries last longer, but because the giant data centers that run the internet consume a shocking amount of power. And then, way out there, is the mind-bending world of quantum computing. We're talking about a whole new way of calculating that could solve problems that are flat out impossible for even the biggest supercomputers we have today.
This quote really sums up the entire philosophy behind how CPUs work. The real genius isn't in teaching a chip how to do one super complicated thing. The genius is in making it unbelievably, absurdly fast at doing millions of incredibly simple things. By breaking every huge task down into tiny steps and then just blazing through them, CPUs can achieve things that seem like magic. It's all about raw speed and efficiency at the most fundamental level.
So from computers that filled entire rooms to processors that sit on the tip of your finger, the journey of the CPU has totally reshaped our world. And as they keep getting smarter, smaller, and more efficient, it just leaves you wondering, right? What incredible new things will they allow us to do next? What new worlds are they going to unlock for all of us?